Okay, that's mean welcome in the week. I believe this is week 4, but this is lesson 3. Okay? That's when we starting chapter 2 this week, and chapter 2 talks about rate of change. And the most important and the new concept is the instantaneous rate of change. Yes, we can see this. Instantaneous rate of change. That means we have to compute a rate of change like exactly at one point, right? And we know that we do have a little bit of like challenge and problems sometimes. And the next section, 2.2, 2.3, they all talk about the instantaneous rate of change, because as you probably learn, the name of the instantaneous rate of change is the derivative of the function, because that procedure or that phenomena, I can say, this particular rate of change is so widely used in science, economics, engineering, any field, that we do have a special name and special notation. That's what we will call a derivative of the function, and the notation is f prime. Okay? And of course, would be nice if we will understand the whole procedure behind differentiation. Okay, that's me. Let's start. As always, I collect a few important questions that I will go through, and I hope the questions gonna be helpful for your quiz, test, and midterm final later, especially for this week assignments. And I also answer a few questions from the discussion board, because I think somebody asked a few questions. That means I will answer. That means let's just see what we have. Okay, I didn't like copy all of the terminology or the new theoretical thing, but just a little bit. That means let's see. Probably I'm gonna read the same that I just said. The instantaneous, like rate of change, or let's say velocity of an object at the time t, is defined like as a limit of the average velocity of the object over a shorter and shorter time, like intervals containing that time, that t. Because if we have to find the average rate of change, no problem. Okay? Like let's say I did travel. I can maybe write something. It's also a test. Let's say I travel 150 miles. Oh, the writing is not as good as my previous laptop. And it took me like 3 hours. Okay, that we can see no problem. I do have my time, I have my distance, and I know what's the average rate of change of the distance over the time, which of course is speed velocity. It's just 50 miles per hour. Okay, I will switch off the video. Okay, hopefully the writing will be more effective. Okay, that we can see that's not a problem. If I have 1 point, if I have actually 2 points, like 2 intervals, I can divide. But the problem is, let's say I was driving for 3 hours, yes, from 0 to 3, of course, that's my time interval. And then I would like, and let's say this is my position function, s at t. Actually, this is the rate of change, which we know the notation, I can write it down. Let's say I would like to know what is my rate of change exactly at 2 hours. Yeah, that's when you can like imagine I'm driving and somebody is like watching me, and exactly after 2 hours, at 2 like hours of my trip, like what is exactly my speed? Okay, and I still need a distance over the time. That means what is really my distance? If somebody will take a picture of me exactly at 2, this will be like motionless. Yes, I am not moving exactly at 2. I am moving like from 2 p.m. to 2.0001 like second later, right? That means I am moving. That means that's the whole idea. We still have to create a really, really short shorter and shorter time interval. And then I can find my distance that I moved from 2 p.m. to 2.0001 p.m. Okay, and then that distance, which of course is really small distance, but and also is really small time interval, but I can still divide and get my average rate of change, but it's not. It's the instantaneous. That's the way to compute. That means this is the thing that we have to like create a really short time interval. And of course, the instantaneous rate of change is called like a rate of change of the function or the limit of the average rate of change. Like limit means that I can compute the average rate of change, but I have to get closer and closer to my point. Okay? And as I said, we do have a special name for the instantaneous rate of change. We do call derivative of the function f at a. And that's the notation, f prime. That means if you see the derivative, the name derivative, this means instantaneous rate of change. Rate of change exactly at one point, at a. And f prime is the notation. Okay? That means we're okay with the terminology and the new notation. What next? Of course, we also mathematically, we know that the derivative of the function at the point A, it's simply equal to the slope of the graph, like how the graph is changing at the point A. That means having like average, like that's what, it's not a problem. I can simply get the line and I can compute the average rate of change, rise over run. No problem. It's like slope of the line, or if this represents distance, this time is the velocity, speed, and distance over the time. Changes in y, changes in x. No problem. The problem is if I have to find the rate of change exactly at one point. That means what is my delta? What is my delta y? This is of course delta x. What is my delta x? What is my delta y? Oh, I don't want to erase. We don't know, right? I mean, we know it's 0 over 0, theoretically, right? I'm not moving anywhere, no rise, no run. And 0 over 0, we do see things like that in mathematics, but from now, looks like pointless. Like I can accept 0 on the top of my fraction, but I can't really accept 0 in the denominator. I can't divide by 0. That means what we're creating? We're creating a tiny, like 0.0001, almost 0, but a tiny interval. Okay, and respectively, we will create like another value on like the difference in the value of the function, the y's. Okay? Which means we're creating a average rate of change, but on the tiny interval, and we will call instantaneous rate of change, almost 0. Okay, that's me what I have. Okay, another information from section 2.1, we probably realize also that if the function is increasing, if it's going up from left to right, of course, then always the slope of the line or slope of the tangent line, or I can say slope of the curve, which is rate of change, which is the derivative. Let me draw something. If function is increasing, okay, then the slope of the tangent, of course, or slope of the curve is positive. Oh, my tangents are not really, yeah. If it's here, it's of course it's horizontal. That means slope of the tangent means derivative. Derivative is positive if function is increasing. If function is decreasing, we can see slope of the curve or slope of the tangent, it's negative. That means decreasing, negative derivative, negative slope, increasing, positive. And if it's constant, derivative is just 0 because slope is 0 and slope means derivative. Let me actually put a. derivative at a, 0. Okay, that's another like graphically what we can say about the derivative, looking at the graph of the function. Okay, and then before I start my questions, because this is my first question, that we now let's start solving the problems. I did just copy this part because if you notice on the discussion, we did have a few questions. That means this is just from section 2.1, like it's not even an example, it's just the explanation. That means somebody asked where this quantity come from. This one. Okay, that means this is the question. That means what we have, we do have a table, we have some scenario, the height of the grapefruit about the ground. And that means after 1 second, time, we can see the table. Time is in seconds, 0, 1, 2, 3, 4, 5, 6. And then we do have a corresponding height, 6 feet, 90 feet, 142, and so on, okay? That we do have time and the corresponding heights. Now, we're asking for the average velocity, first of all, on the interval from 0 to 1. That means no problem. We can take the average velocity between 0 and 1. It will be s at 0 and 1. S at 1 minus s at 0, 1 minus 0. The value for 1 is 90. The value for 0 is 6. Of course, this is 1. 84. That means 84, which I'm supposed to see this somewhere, yes. 84 feet per second. That's the average speed, average velocity between 0 and 1. Okay, now, let me remove this one now. They're asking for the average between 1 and 2. That means the same thing. S at 2 minus S at 1, 2 minus 1. S at 2 is 142 minus S at 1 is 90. Oh, my writing is not clear at before. Okay, and I believe 142 minus 90, it is 52 feet per second. Okay, that means this is the average between 0 and 1, 1 and 2. Now, what they also have here, they're trying to, okay, now the next question. Are they asking? Yes, that's me now. How can we find the velocity? How? Oh, I didn't mean to do this. Okay, I'm back. Now they're asking how can we find the velocity exactly at 1? Okay, that's what I'm saying, exactly at 1. Like I have only 1 second and the height is 90 feet. And no rise, no run, no changes in y's, no changes in time, no changes in the height, the time and the corresponding y values. Okay? That means that we can see that's where the problem starts. And using the data that we have just available, what they did, they kind of took, they took these two numbers, 84 and 52, because that's the average rate of change before 1 and after 1. And they took the average of this, 84 plus 52, dividing by 2, I believe this is 136. Oh, my writing is not. And this will be 368 feet per second. That means this is like just the approximation. And I can say this is the, it's not exactly at 1, but it's the approximation because it's at the moment is the average. The perfect way will be this. Can you see? And now we do have this tiny interval. That means I will just move from 1 to 1.01 or even closer, 1.0001, because I have to create almost no run, but I have to create a run. Okay, that means now, if I would like to create, let me do this, 1.01 and the value at 1. Oh, I don't like this writing. And difference in times will be this. That means that's not a problem. Okay, that means let's see. And we can see they do have the value because somebody asked for that value 90.678. That means what I'm assuming where the value come from. Since this, it's approximation. I mean, I would say the right-hand side of my equation, if this is my equation, it's more accurate. But of course, I don't have this value. What is exactly the height at the point 1.01? That means what I'm assuming that they did create 1.01. We know S at 1. S at 1, the height at 1 second is 90. And this will be 0.01. And we know that this is approximately 68 feet per second, the rate of change. Because that's rate of change, instantaneous rate of change, and this is the approximation. And now I can try to solve. That's what I figure out. I can solve this equation for this value. Let's maybe name this x. Then maybe we can, like a x as an unknown. Okay. Oh, I can say x is the value. Oh no, we don't have x, we have t. Okay, we can use x. That means x will be equal to, of course, x is my value that we're looking for. X is this quantity, that's the x. Okay. I will multiply 68. I will multiply 68 times 0.01 and add 90, right? If I would like to solve this equation. And we can see it is 90, and I have to move the decimal points. It will be 0.68, adding 8. Adding to 90, that means that's where the value comes from. The value of the function, the s at 1.01 is 90.68. They have 6, 7, 8. I think it's close enough. That means that's what everything on this slide is like approximation. And the main idea is to understand like what exactly the instantaneous rate of change means. The rate of change, the velocity at one point. And as we can see, that's how they figure out, because they figure out based on this 68. Okay, that's my answer to this question. I did create the ratio, the quotient, which represents the instantaneous rate of change, and I did have approximation. I use this to get the value which is not provided in the table. Okay, if you have question, you can ask, but I hope this is clear enough. It is still, we still have to like think about this instantaneous rate of change. It is a little bit challenge, but hopefully going through all of the problems today, we will be more confident. And I also found, let me check. Oh, I didn't copy this. Okay, thank you. I was just, okay, don't look at my questions. Oh, where is my, because I did have one question. Okay, oh, I think this one. Oh no, maybe, okay, let's go step by step. Okay, because I will not miss anything. I was just changing the order of the questions. This is not, okay. So now let's start. Just one more comment. I think on the discussion board was another question asked, but I did have this question later, okay? That means I will answer the question. Okay, that means let's start. Why this is not, hang on. I'm just trying to Oh, yes, now it's done. Example, question number one, example number one. A function f is given below, and at which of the labeled points f prime is positive, negative, and 0. And at which label point is the f prime the largest and the most negative, right? That's when we will answer. We have to find the highest value and the lowest value of the derivative. Okay, that we can nicely see. I can add some labels. Okay, A, Y, and X. Okay, that means let's look at the point A. The point A, and what do you think? Maybe you can answer first. What do you think? What will be the value of the derivative? And I can say at A. Because theoretically, I should say this is A. The corresponding A, big value corresponds to the X value A. Okay, that's what do you think? Can you give me an idea? Is this value positive, negative, or maybe 0? What do you think? No idea, no even, can somebody, yes, it is negative. Thank you. And no, I can't say the name. Okay, that means it is negative because we have to remember this. Derivative represents the slope of, we can say the curve, or slope of the tangent line. Maybe I can write slope of tangent to the curve. Of course, at the given point, let's say at A. That means, please remember, derivative graphically represents the slope. And we also learn that if the function is negative, of course the slope is, no. If the function is decreasing, then the slope is negative. And drawing a tangent line, we can see, like, we can maybe approximate. Slope will be quite steep, I don't know, -2, which means derivative, it's equal to -2. Okay, what about B? Can you tell me what is the value of the derivative at B? Oh, that's quite easy. Do you see the line? Do you see the slope of the it's 0. Horizontal lines has the slope 0. That means at B is 0. Now we have C, D, E, and F. Okay, now C will be like that. That means, what do you think? What is the derivative or the slope of the tangent at C? Do you think it's positive? It's positive, thank you, Craig. It's, I don't know, let's say half. This is really just approximation. If you will say 1.3, it's also good. It's definitely less steep than this one. This one was negative, but steepness. Okay, let's keep moving. D. What about derivative at D? Derivative at D again, thank you, it's 0. You see, that's we can nicely approximate. Okay, what about E? That's my tangent. My writing, it's derivative at E. It's definitely negative. Let me draw it again. Do you think it's more steep or less steep than at A? I think it's a little bit less steep. That means, let's say -1. Doesn't matter. We really have, I can put -1.5. It's just to compare. Okay, and at F, I'm not gonna even ask. The value at F is 0, but at G, can you tell me the value at G? I can write G. At G is positive, and maybe 1, I can say. Okay, that means that's how we can get the values. Looking at the graph, and if question asks for the derivative, remember slope of the tangent. You can kind of like draw a tangent and approximate the slope. Rise over run. Okay, that we do have answer A. That means which one is the largest value? Which one is the largest? Looks like this one, right? 1. 1 will be the largest one because it's the most steep positive, right? And the most negative, okay, that's when we did start with the smallest value and we finish with the largest value. Okay, let's keep moving. Hang on now. Okay, now I wanted this question. Because we can see this is multiple choice, and I don't want you like to be like confused on the test. That means this looks like one of our test quiz question. And let's see if we can approximate, because it's the same thing. If we can approximate the whatever they're asking. I don't want to say too much, and if we can pick the right answer, because that's what you're probably going to be worried. But let's see. The following figure shows a graph of f of x. Okay, the blue is f of x. Estimate the instantaneous rate of change, we know what it is, of function f of x at 5. That means instantaneous rate of change means derivative at 5, right? And this is slope. I can say of slope of tangent. My writing is terrible. That pen is not doing good job. Okay. Okay, and you can even see, yes, I did draw a tangent for you, and this is 5. Okay. Oh, we do have an answer. Okay, let's see. And that means I have to just find the slope of this line, which I can use some approximations. That means what we have, I can actually compute rise over run. I think negative 3/2. Okay, let's see. I can change the color. Yeah, which color? Maybe green. Green. Okay, that means I have to compute. Let's say this is also 5, maybe a little bit more. Okay, that means slope of this line is simply changes in y over changes in x. Changes in y, which is rise, will be 5 minus 2, and this distance is just 5 minus 0, which this is, no, something is wrong, because the line is going down. Where is my mistake? The corresponding, I have to have, okay, 5, okay, come on, I can't, of course I can do this. This is 3, and this is 5, right? Because it's from 0 to 5. And it's going down, that means it's negative 3/5. But why I can't get the negative from my calculation? Okay, that's not a moment that I want to confuse you. Okay, we can see that we're going 3 units down, right? From 5 to 2, and then 5 units to the right. Of course, it's negative 3 and 5. Okay. We understand this. Okay, that was my point. Negative 3/5. And you can see probably probably that 5 is not, maybe it's a little bit more. That means probably I did a little bit like underestimation, but still I've got a fraction right away from my graph. And now which answer you will pick? Or let's do this way. Which answer is definitely not an answer? Let's say A, B, C, D, and E. Which one is D? Right, thank you. That means D is definitely not the correct answer because it's positive. And now, do you think C is the right answer? They are not the same distance, right? Because we can definitely see this is 5 units And this is only 3 units. That means it's not the same. Also, it's not as steep as -3. Okay? And actually, do you think A is more than 1? We definitely have a fraction less than 1. Definitely. That means I will also erase this. And the only option that stays is this one. That means this is one of the way to kind of like get the idea. We don't need to have exact number, but just in case if they don't match to our approximation. But what I can do, I can write my answer, I can write my option, and I can try to get, that's not my option, this is my option, and I can possibly find a common denominator, which will be 15. I can multiply by 3, and 15, I can multiply by 10. That we can see -9/15, -10/15. They are almost the same. And as I said, my quantity 3, this one, it's a little bit underestimation because I think this is a little bit more than 5. Okay? That's another way to compare. But please don't worry if you can't get exact value. I'm sure you will eliminate everything which definitely doesn't work, and you will end up with one answer. Okay, that's just the warning, but you will be good. Okay, and I think I did skip one question. Okay, the same thing. Let's maybe do half of this question, or maybe we can estimate all of them. Estimate the derivative of the function f of x graphed in the figure below. This is from your textbook. And we want to look at x equals to -2, -1, 0, 1, 2, 3, 4, 5. And I think at -1, the job is done for us. That we make sure that you know these values. This is y. And this is x. Okay. And I need a pen. And at -1 looks this point, right? At -1. And we can draw a tangent and find the slope. That means the approximation is the slope will be rise over run and looks like 2/1, 2. Okay, let's maybe pick because we don't, it's too narrow. Or let's say the value 1, 2, 3, right? You can nicely see the derivative at 3 will be slope of that line and looks like 1/2, -2/2, -1, right? The slope is this. Which one we can compute? Maybe we can compute at 1. What do you think? At 1, I can draw a tangent line, maybe like that. Oh, not really. And we can approximate. That means, what do you think? At 1 will be, looks like I have to take that down and this one. Maybe also like 2/1. Derivative at 1 will be -2/1, -2. And that means it's just the approximation. You can try to solve these values. Okay? And again, don't worry if you will get exactly actually I can be a little bit more precise. Oh, I'm sorry, I have to switch off. Okay. That means because I think this question was asked. Don't worry if you're not getting the exact values. Actually, I should be a little bit more because I can say it's 3 and 1.5. 3 and 1.5, which of course is again -2. Maybe 4. No, I didn't want to draw. 4 is actually here. That means 4 will be, it's not symmetrical, but at 4, I think will be a little bit less, maybe also 1, if I will, because we can, oh, that means derivative at 4, it's also 1. And we can see everything, it's like at the moment approximation, because we want you to understand slope of the tangent line. And I did put the values, you can check, you can try to estimate, and you can try to get these values. But don't worry, I don't think we can get 4, because that's the derivative of the corresponding x value. Let's see actually 5, okay? 5, because that's what the textbook is providing. Quantity 5 is here, and I don't even know how function behaves, but it is quite steep. Okay, that means maybe it's derivative at 5. According to that table, it's 4. Maybe 1 over 4 rise over run. Okay. But we can see we have to definitely recognize if it's positive or negative, if it's 0, or if it's positive, like it's really steep, it's not, we can and always think about rise over run. If it's going up, positive, if it's going down, negative. Okay, let's see what else I have. We did this one. That means my next question is, we do have a graph of the derivative. That means this is f prime, right? And which of the graphs, A, B, or C, okay, is the graph of, oh, no, this is graph of the function. The graph of the function is given. And now we have to figure out which of them, A, B, or C, is the graph of the derivative of this function. Right? Because we know how to read what derivative is telling us. Okay, let's start. We do have a function. I will always start with the horizontal tangent lines. That means at this point, we do have horizontal tangent, and at this point, we have horizontal tangent. That means at, okay, like -1. Okay, -1, and this is 2. That means, what do you think? We know something. What is the value of the derivative at -1 and at 2? What's the value of the derivative at 2, and what's the value of the derivative at -1? Of course, they are 0, right? That means 0, 0. And then I'm looking. This one has 0 here, 0 here, and 0 here. That's wrong. This one has 0 at -1 and 0 at 2. Possibly, but let's look at this one. 0 at -1, 0 at 2. That means based on that information, I only eliminated A. Okay, let's see B and C. Which one, what else we can do? Now what we also know, we know this. If function is decreasing, okay, because this is decreasing, what's the value of the derivative? This is decreasing and this is decreasing. Do we remember? The derivative is positive or negative if the function is decreasing? It's negative. Okay, that means f prime must be less than 0 and f prime must be less than 0. In order to graph this, in order to look at the graph, derivative must be placed below the x-axis, right? On that interval and on this one. That means, let's look at the B option. Derivative is actually placed above. Yeah, that's not good. Oh, that's funny line. But we can see the option C. Derivative is below x-axis. Derivative is negative. The value of this, because that's the value, that's the derivative, is below. Because negative means below the x-axis. We know what this means corresponding, like respectively to the function. That means this looks good. And if function is, let's use this. If function is increasing, the derivative is positive. That means that's positive above above the x-axis. We can also investigate like the slope, right? Because you will probably think, why do I know that that's the shape? But we can see that the slope is like that, okay? And then it's getting bigger and bigger, and I think this is like the steepest point, right? The steepest point, the biggest average rate, instantaneous rate of change. And we do have this biggest point. And then again, it's getting less steep, and eventually it's zero. Yeah, that's what we have. It's getting bigger and bigger, and then attaining the maximum value of the slope, and then getting back to zero. Yeah, that's how we can plot the points. Okay, but we did found the derivative, okay, of the function. Remember, always horizontal tangent, the value will be zero, and increasing, decreasing concept. Okay, I have a little bit of solution. You can read this later. Okay, now it's the same question. Let's just do one more. Graph the derivative of the given function. That means now we don't really have the derivative. We have only a function. Okay, and we have to figure out the shape. I mean, I'm just trying to, okay. And let me maybe do underneath. This will be, it's not a proper, this will be the derivative. That means let's start. Horizontal, 0, horizontal tangent, 0. That means at this point, derivative must be 0. Okay, derivative is, oh, my dots are terrible. It's not even the dots. Okay, and now, what do you think? Between these points, I don't know what other points. Let's say -1 and 1. They are a little bit -2 possibly, and 2. Because, okay. And then what is happening between -2 and 2? Can you tell me? Is the function increasing or decreasing? Between -2 and 2, this one, is function increasing or decreasing? It's decreasing. That means if the function is decreasing, what is the value of the derivative? The derivative is negative or positive? It is negative. That means I have to place the graph of the function of the derivative below, negative. And we remember that shape because it's from 0 slope, a little bit steeper, attaining a maximum value. It's negative, but it's the steepest in the negative direction, of course. And then again, it's getting less steep, and going to 0. Okay, that means this is that part. And this one will be easy. The slope is definitely positive, and it's big, and big. That means big. And this is almost the mirror image. It's also positive, but it's getting from really steep to 0. From really steep to 0. Okay, that's the graph of the derivative, just using a slope of the tangent, slope of the curve. Okay. And I will skip this because that's the same questions. Okay, that's to interpret the derivative as a slope of the tangent line. Yes, slope of the curve, we can say. Okay, now we do have example number 7. We have to estimate the derivative, but numerically. Let's see. Estimate f prime at 2 when f of x is defined as a e to the power of -12 x, and using the values 2 and 2.001. Okay, that means this will be good approximation, because I can say derivative at 2 is defined as a value of the function at 2.01 minus the value of the function at 2 all over this difference in the x values. And that means this is simply delta, changes in y, changes in x, on the really tiny interval, which means it's the instantaneous rate of change, because we can see we moved just a little bit. Okay? Okay, that means this is purely like calculator question. I will have 0.001, and the value of the function for 2.001 is e to the power of negative half, and we have to substitute 2.001 minus e to the power of negative half times 2, because that's the value at 2. And I did use the calculator. You can probably do the same, and I've got negative 0.18. I don't have the particular values, but we can see we only have to do this. Also, one of the questions on the discussion board was the same, like somebody was, I think I did type the solution, but somebody was asking, how did we get these values? We are using simply a formula. Okay? That's when we're using the given formula instead of x, we're substituting this, and we will get corresponding values. I don't have these values, but I have the final answer. Okay, as we can see, that's nice and easy question, but still the same concept, still the same idea. Okay, let's do another one. That's also from your textbook. Using slopes to left and the right of 0, estimate r prime at 0. If function is defined also as exponential, 100 times 1.1 to the power of x. Okay, that means they actually, now we can see we don't know how far. We have to estimate the rate of change at 0. Okay. The previous question, I can come back. The previous question asked for the derivative at 2, but we knew how far we can go. They gave us the tiny interval, 2.001. This one is not giving me, it's just asking me to find the derivative at 0. That means I will make the decision. Maybe I can move also 0.001. So let's see. From the left, how can I, maybe let's do this first. That's x, that's 0. Okay? However the function looks like, I have to find the slope of the tangent. Actually, it is exponential function. It means it's not difficult to draw. And at 0 is the value, actually we have 100. That means it's 100 at 0. Okay? This will be a function, and that's the x value. And this is the function, that's the function. Because if I substitute instead of x 0, right, 1.1 to the power of 0 is 1, times 100 is 100. Okay. And we're looking for the slope. We're looking like, what is the, I think the line is a little bit more steep, but it's okay. We're looking for the slope of this line. Because the exponential function, it's growing extremely fast. That means this should be much, much steeper, but I can leave it like that. Okay, that means 0. And I will try to go to 0.001, okay? And I will try, because they want to go to the left and to the right, and negative 0.001. That means, first of all, let's focus on the interval between negative 0.01 up to 0, okay? And we will get, and this will be my left. That's my left-hand side approximation. And the approximation of the derivative using that interval, it will be value of the function, actually it's r, value of the function at 0 minus the value of the function at negative 0.01, and then 0 minus negative 0.001, okay? Which of course we will be adding, because we can see the run is just that units. Okay. And in order to approximate this, we will have 100 and 1.1 to the power of 0, 100, 1.1 to the power of negative 0.001, all over 001, which we have to use the calculator, and I did, and I've got 9.531. Yes, if you will get, this will be 100 minus, this will be a little bit less, and then we can get the value. Okay, but we can see the same idea, creating a tiny interval and computing the average rate of change. So now, using the right hand side interval, I will go from 0 to 0.001 on this side, to the right hand side. 0.1. No. And then the same thing, approximating the derivative, it will be the value of the function for 0.001 minus the value of the function at 0, and then always corresponds to this value minus this one. And I will skip my writing. This is also 9.531. Actually, that's what you can check. You can use the calculator and you can check this. Because we can see it's really almost, if I will draw a secant line, they will almost give me the same slope. Normally, when we're getting a little bit different values, we can add them together and divide by 2. Simply get average. But that means this is good approximation, 9.531. But we can see the idea, okay? What they asking. They didn't, and what I did, I picked that value, 0.001. Yeah? You can only pick 0.1, maybe. Yeah? You can move 0.1. It will be also good. Yeah? I just decided to do this way. Okay. That's the explanation. And another question, because we can see all of the questions are about the instantaneous rate of change. From the graph, from the formula of the function, from the given values, like now we will try to do, everything is like an approximation. Okay, that's mean table 2.6 gives the value of C at T, the concentration, it's the milligrams per concentration of the drug in the bloodstream at the time T. Okay, that means this is a milligram number of grams in that concentration. The concentration, I can say concentration, I don't really have to, yeah, in milligrams. And the time is in minutes. Okay, that means construct a table of estimated values for C prime at T, which is the rate of change of the concentration with respect to time. That means how this concentration of that drug in the bloodstream is changing with respect to time. As we can see, at 0 minute, we have that amount, right? At 0.1, it's a little bit more, 0.89. At 0.2, 0.94, 0.3, 0.98. And at 0.4 and 5, we can see it's 1. And then at this point, this is 1, as we can see, it was increasing. And then 0.97, 0.90, 79, and so on. That means it's increasing and decreasing. Yeah, that's one observation that you may have. We may notice that it's increasing or decreasing. Okay, that's what we will do. We will probably not compute for all of the values because they ask us to add one line in that table, and this will be C prime at the corresponding T. Let's maybe compute some of them. Okay, and then you will just, because it's a few numbers, 10 numbers or 11 numbers. That means let's try to find out C prime at 0. And we can see we can only go to the right hand side because we have only these values. That means C prime at 0, I will use that interval. The value at the concentration at 0.1 minute minus the concentration at 0. That's, I'm just creating 0.1 minus 0. That means this is 0.89 minus 0.84 divided by 0.1. This is 0.05 divided by 0.1, it will be 0.5. And I can say this milligram concentration per minute, per 1 minute. Okay, that means 0.5. And again, we see how I use this. That means this is 0.5. Yeah, which one can we let's see C at 1. Not C at 1, C at 0.1. I can just go by order. That means this will be C at, and I'm moving for this one, I am moving on that interval. That means C at 0.2 minus C at 0.1 over the difference, 0.2, 0.1. This is again 0.1 because they're changing. We have the same time intervals. And at 0.2, the value is the corresponding value 0.94 minus 0.89. And this one is, again is 0.5, 0.05 divided by 0.5. Okay. And it's the same, milligrams, the concentration per minute. And this is actually correct, one of the things, because we remember this is positive, 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 right? Probably here, what do you think? What we will have here? At 2. Can you see this? Probably I can't really figure out at 0 because I will be subtracting 1 minus 1. Right? That means I will definitely have 0 here. I mean, this is the moment that derivative is increasing, function is increasing, horizontal tangent 0, and then is decreasing. These values supposed to be negative. Okay. We can compute maybe one of them, maybe C prime at, which one? At 7, 0.7. Let's see if we can get negative. I will get the value at 0.8 minus the value at 0.7, value at 0.7, and the difference. Okay, at 0.8, no. At 0.8, we do have 0.79. At 0.7, just 0.90. And this is still the same difference, 0.1. And this one is 11. No, 1 point. What's the difference? The difference is, am I crazy? 11.11. That means it's 1.1. Negative, of course, negative. Am I right? I think so. Because we have to move 1 decimal point to the right because we're dividing. Dividing by 0.1 is multiplying by 10. 1.1 negative. That's what I wanted to. Yeah, it is. Oh, okay. That's and the same, of course, the same units. That means make sure that having a data, you will know how to get the derivative. And you can go either way, right or left. Yeah. On this one, I went right only. I moved from 0 to 0.1, from 0.1 to 0.2, and so on. Okay, and I do have, of course, I have the solution for you. You can check the rest of the values. Can you see the table below? We do have, that means I did compute this one, and I did compute this one. My writing, it's terrible. Okay, I can't even erase this now. Okay, and I think we kind of look at this, that the difference was 0. Okay, that means we should be okay with this one. Let's keep working. Actually, this is the same question. We have to estimate f prime at 4 having these numbers. That means what we will do, I will go from 4 to 5, okay, and I will go to the left from 3 to 4. And you probably, okay, you have to just get the value at 5 minus the value at 4 and divide by the difference. The difference is 4. That's mean corresponding value of the function f at 5, it's 11.7 minus 8.9 dividing by 1. 11.7 minus 8.9, 2.8. Okay, that's the right-hand side, right? Right-hand side. And this is f prime at 4. 4. Okay, now f prime at 4 using the left-hand side, the value of the function for 4 minus the value of the function at 3, and the difference. Difference, of course, is 1. For 4, again, is 8.9 minus 6.4. 8.9 minus 6.4, 2.5. Okay. And what we can do, we can add them together and divide by 2. If we would like to have the average, I mean, even more. No, 2.8 plus 2.5 divide by 2. 2 and 2, 5.3 divide by 2, 265. That's me close to the both of them. So we can see that's what we can do with this estimation. And that's the average. Okay. Okay, we do have this. Maybe you can answer this. Let's see what we have. The following figure is the graph of n equals to f of t, the cumulative number of customers served in the certain store during the business hours one day as a function of an hour of the day. At what time was the store the busiest? That's what do you think? The rate of change, of course, we're looking, yes, the busiest store is when the rate of change of the total number of customers is the maximum. That's what do you think? Can you approximate? It's quite good. At which time is the I don't want to say the highest rate of change of that curve? Approximately, do you think you can tell me? I hope you are still there, because I was like calculating. Okay, Sean said 1. I think it's a good, yeah, I think this is the point. Because we can see this, the rate of change, the slope, it's not really steep, it's getting steeper, steeper, steeper. And I think, right, this is the steepest point. And it looks like 1, and we even have the number, okay, 200. I mean, we can compute the rate of change, of course, but that's the, yes, at 1 p.m. That means the store is busiest when the rate of change of total number of customers is maximum. And this is where the slope of the curve is the steepest. And this is happening at 1, exactly at 1. That means I can write that the value of the derivative, the rate of change at 1 is the largest. Okay, has maximum, which means is the curve is at its steepest position. Okay? As we can see, is my writing good? Because then again is getting the rate of change, it's smaller and smaller. Okay, that's mean 1 p.m. Oh, okay, we do have, I typed this for you. Okay, now what we have, I copy some for you, the interpretation. Yeah, I think we don't have to really, it's the same, it's still the telling us that the small interval. That's how we can compute the derivative and some units, but we know that. And now let's keep working on the derivative, having some different scenario. Okay, the cost of extracting T tons of ore from the copper mine is defined as a function f of T. T is tons and C is cost in dollars. What does it mean to say that f prime at 2000 is 100? Okay, that's we have to know how to interpret the derivative. That means f prime, okay, f prime at 2000 is 100. That means first of all, C is the cost. It's the cost in dollars. T is a number of that ore in tons. That means this is amount of ore in tons. Okay, we do have this. And derivative, oh, we do have the answer. Inger said, the cost of $100 to extract 2,000 tons. Exactly. That means when 2,000 tons of the ore has already been extracted from the mine, the cost is 100. Of course. Thank you very much. That's excellent answer. That's what I was trying to. That's what I was trying to say. That we can say it costs $100 to extract 2,000 tons. That means I can say derivative. Okay, it's simply like the units will be, because it's the derivative. Let me I wanted to write for you. Will be the rate of change of cost with respect to the rate of change of cost with, of course, respect of with respect of change of T, but T is the number of tons. That's this, and it's dollars over amount tons. That's been $100. Of course, it's but we can see this is, okay, this is the rate of change. That means $100 per ton. And what we can say to estimate, like it costs about $100 to extract the next ton. Okay? That's like, let's say 2,000 first ton. That's the interpretation. That means when we extracting 2,000, the cost to the next ton is approximately $100. Okay, that's what I was gonna say. Because it's not, hang on, because I'm trying to, Inger said it cost $100 to extract. Oh, no. That's what I'm trying, that's what I'm talking to myself. No, that's not your explanation, Inger, is it cost $100 to extract 2,000 tons. That will be something different. Right? This will be just this. Right? If we have 2,000 tons, it will cost 100. Right? But we can see that's not a prime. That means the explanation that you said, I think you said just to the value of the function. Okay, if this will be given like that, then you can say, right, okay, that we have to be really careful. That means we definitely have rate of change. That means this box, which I will erase in a minute, means that the value of the $100 cost 2,000 tons. Like if we would like to extract 2,000 tons, we have to pay 100. But that's not what we have. Okay, we do have f prime. That means one more time. This means that when 2,000 tons of the ore has already been extracted. Okay? Then the next, the price for the next ton, it's $100. I mean, I can maybe write it, because just in case if you have to pick options, or you will have similar question. It costs, my writing, about $100, okay, to extract the next, because it's the rate of change. How the price is changing? $100 per 1 ton. The next ton, and I can say 2,000 first. Okay. The business and finance majors will learn that as a marginal cost. Oh yes, of course, we will. I think the second part of chapter 2, we will take all of these derivatives and instantaneous rate of change, and we will put, yes, like we will look from the finance perspective. We will definitely have the marginal cost, of course. Yeah, Charlene, thank you. That's the good comment. But Inger, it's still good. Try to answer a question during the class. I really appreciate. Okay, that please remember is the cost of the next. Yeah, no, it's good. It's like in normal class. We asking question and we making some mistakes. That's our learning curve. Yeah, that's actually good. That means, look, we have to know that it's the rate of change. It's not just the dollars. It's the dollars per 1 ton. That means hopefully this explanation is good. Okay, but yes, this will be the marginal cost. Really good. I didn't want to mention now. Okay, and we do have 2 things. One thing is, that's the solution. One thing will be something like that, the tangent line approximation. That's what we kind of did, because the tangent line represents the slope of the curve, and instead of looking at exactly the slope of the curve, we are looking at the slope of the tangent. But let's see how we can use this. That means we do have an equation that probably we have to remember, and we will call like a local, like a linearization. I can say L of x. Okay? And what we have to know the value of the function at a, and then derivative times delta x. We do have some bigger explanation of this, but we don't really have to know. The only thing that I like you to show is this. Let me draw a function, for example, something like that. And then I can draw a tangent line. Let's say this will be 8. Okay, this is t, and this is f of t. I think it's f, okay. And I would like to draw a tangent line at 8. Okay, okay. That means what happens, sometimes I can have it's much better to get the information, of course, on the function, but instead of using the actual curve, I can actually use the tangent line. And this is the equation of the tangent. I can use the same color. The blue line, this will be the equation of the tangent line. Okay? And it's simply mx plus b, but has a little bit different form. That means let's maybe solve this problem, and we will see how we can apply this. That means one more time, instead of taking an actual curve or actual like data points, like you will probably have some experiment maybe you will do one day, or some finance information, and you have like lots of data, and you can fit the line. Yes, you probably know, like the linear approximation. Instead of taking this weird curve or this all of the points, you can fit the line, and that line we call linear approximation. Okay, let's look at this question, and hopefully we can understand this better. Annual net sale in billions of dollars of the Hershey Company, the largest US producer of chocolate, is a function s f of t of time in years since 2000. Okay, 2000. Now we have to make an interpretation of the statement f of 8 is 5.1. F prime at 8 is 0.22 in terms of Hershey sales. And then estimate f of 12 and interpret this in terms, again, of the Hershey sale. Okay, that means this one, probably it's not a problem. F of 8 equals to 5.1. Okay, now who can give me the explanation to this? F of 8 means f of 8 is 5.1. That means 5.1 is the sale, and of course it's in billions, okay? That means the sale is, I can write, you can try to maybe type the answer for me. This is not a derivative. That means, yes, of course, it was 5.1 billion in 2008. That means that's my point also. 8 means that we did move 8 years since 2000. That means in 2008, the sale was 5.1 billions. Wow. Billions of dollars, of course. Okay, that we do have the interpretation of this. Now, who will try to make the interpretation of f prime at 8.22? F prime at 8. I can still say in 2008, because that's what it's telling me. And what prime means? Prime is simply means the rate of change. That means how the sales is gonna be changing, like during the next year in 2009. Okay, that means in 2008 the rate of change of the sale. I can even write this. The rate of somebody writes, Sean, sales will increase by $0.22 billion in next year. Exactly. That's actually really good explanation. The rate of change of sale is $0.22 billion per 1 year. But actually, I like your explanation that will increase by 0.22 billion in the next year. That means probably in per 1 year. Do you think you can estimate f of 9? What will be the f of 9? Oh, that's actually nice. Because we can f of 9. What will be the value? What will be the sale in 2009? It's 5.1 plus 0.22. Really good. 5.32. Okay, shall we keep working on this? We can keep adding because they're asking us to estimate f of 12, which I do have quicker of, but we can do this. What about f of 10? Who can give me the value? What will be the sale in 2010? 5.1 plus, okay, the rate of change, and times 2, because we're changing the rate of change. I mean the time. It's 2 years. Who can give me the final answer? Who can do the math for me? 5 point. Oh, why I keep changing? Oh, come on, we are here. You can multiply 22 times 2, I mean 2.22 times 2, and add to 1, 5.1. Or who can type? Maddie type 5.32. Are you still there? Because Yeah, I think we do have quite crowded room today. 80, 98? Okay, that's the thing. Like, can you see my graph? I am assuming that yes, because that's my approximation. That's what I was trying to. We assuming that this rate will change. No. We assuming that this rate, based on that rate, we're trying to estimate this. That's actually what is the tangent line approximation. Even if, and we can see my let's say this is the function. Let's say this is the sale. It's like increasing, and this is my rate of change. That means exactly at 8, it's like that. But I can assume maybe it's a little bit slower. We can see if I will draw a tangent here, the rate of change will be a little bit less. That means the sale is not as big as at 2008. But that's what we're doing. We're doing this approximation. That means instead of getting that value as a sale, this value as a sale, I'm getting this value. Because I'm using my blue line. I'm using my, where is my blue? That's my blue slope, the slope of the tangent line. Okay, that means in 2010, we will get 44.54. Did you write? Yes. Okay, Maddie, yes, I think that's what we have to think. That's actually the whole idea about linear approximation. Okay, that means maybe I can skip one. Who can tell me f of 12? F of 12 will be 5.1 plus the rate of change. Oh, somebody computed for us. 5.1, 22, and how many years I have to multiply? Because from 4, thank you, Sean, thank you for helping me. That's why I have to multiply by 4 and then add to 5.1. Oh, 88, 98, yes, Maddie, thank you, you're right. That means I can write my answer that f of 12 is 5.98. Okay, that means this is the sale. Of course, using 2.2. And now, because that was my point, writing down, let's look at, even this equation. Can you see 5.1? 5.1 is just the value at A. Now I'm trying to make a sense of this equation. 0.22 was the rate of change. Okay? And delta X is telling me the difference in times. That means that was 4, that was 0.22, and this was, I promise I'm not doing these changes, it's just the laptop. And this was 5.1. Let's just keep changing. Okay, one more time. This is my value, 5.1. This is the rate of change. And that was number of years. Okay, at 12. As we can see, we did the approximation. Okay? And this is the final answer. Okay, that's how we can use it. Okay, I think I have one more question and we will be done. That means the last question, also important in this week, the relative rate of change. That means not just the rate of change. I think now you're so confident, the relative rate of change. Relative rate of change is just the ratio. We have to compute the rate of change, like a derivative, and find out how this rate of change is related to the actual value. And that we will call relative rate of change. Yeah, that's the only thing. Derivative at A dividing by the actual value at A. That's it. That means just please remember this and you will have no problem. That's me what we have. I have last question and let's see if we can get this relative rate of change. The number of active Facebook users hit 175 million at the end of February 2009 and 200 million at the end of April 2009. Right? From February to April. With T in month, since the start of 2009, that means we can see of course, April will be 4, February is representing 2, the second. Let f of t be the number of active users in millions. Okay, that's number of users. Estimate f of 4 and f prime at 4, and relative rate of change of f at 4, and give the interpretation of the answer in terms of Facebook users. Okay, that means what we have. You have to help me, of course. That means f of t, it's simply a number of active users. Okay, number of users. Okay, that means they asking us what is f of 4. Oh, because estimate f of 4. Can you tell me what is f of 4 first of all? And they're not asking f of 2, but I also would like to ask you. That means how many users we have at 4? 4 is the 4th month, up April. That means how many users we have at 4? 2 million. Thank you. Really good. I will put 200. I mean 200, not 2. 200 million users in April. Okay. In April. And then, respectively, what is f of 2? F of 2 is 175. Really good. Okay, you understand this. 2 means the second month. Okay, February. Okay, we okay with this. Now, what we have to do? We have to find out f of 4. F prime. What is the rate of change? Okay? Rate of change of the users on Facebook at exactly in April. That's what I have to do. Okay, I will of course estimate the rate of change of the users with respect to time, with respect to change in time. And the only values that I have to go backwards. That means I have to get the value from only February and April, 2 and 4. Normally it will be good if I will have like April, that's the last day, like May, let's say May 1st. Yeah, that means I will have like a fraction, but I can't create tiny time interval. I have to go by using these 2 months. Okay, that means number of users in April, 200 millions minus 175 and divide by 2 months. That means the rate of change is 25 over 2. 25 over 2, it's 12.5. But 12.5 on 12.5 million users per month. Okay, million users per 1 month, yeah, because it's a rate of change. It's the rate of change. Okay, that means it's 12. That's the rate of change. That's what if we will be expecting, like trying to estimate the number of users. That's not a question on this page, but I would like to ask you, what will be f of 5? Do you think you can give me the estimate number of users in May? What you will do? You will simply add, right? You will add 200. I was looking for that. You will add 200, and that's the approximate rate of change. 212.5 users. Millions. Okay, we know that. Okay, but now the last thing that we have to do is the relative rate of change. That means the relative rate of change. How can I write? I can write actually a relative rate of change, because we don't really have a special notation. In April will be the rate of change over the value of the users, I mean number of the users, value of the function in April. That means this one is 12.5 million users per 1 month, and this was with respect, like what is the ratio with respect to 200 users. And I did the math, and it is 0.0625, which means if I will put the percentage, relative rate of change will be 6.25%. That means this is like how this is related to the number of users. And that means the rate of change is 12.5, but with respect, what is the percentage of this rate of change with respect to the actual number that it was in April, 200? 6.25%. That means that's the relative rate of change. Okay, that means that was my last question. And I'm really sorry because I was trying to, I think my writing before was much, much better. That means unfortunately my old laptop works much, much better with the writing. This writing, it's really, really sloppy. But I think the audio works better on this one. That means now I have 1 week to figure out how to combine good writing and good audio. Okay, that means thank you for today. Thank you very much for participating. Okay, and thank you for being with me. That's really, really, and I know that it's really helpful to attend the live session. Okay? That means thank you.